Combinational circuits, design methods, how to design combinational circuits. This is covered in chapter 4 in Maury's manual. We should know that we have two classes of logical circuits. There's something called the combinational circuits and something called the sequential circuits. What are the difference between these two? In combinational circuits, the circuit consists of inputs and outputs. Now, the outputs are dependent on the present input. Each output depends entirely on the immediate input, on the present input. It has no relation with the past input. While in sequential circuits, we have feedback from the output into the input through a memory. So the output does not only depend on the present input, it also depends on the past input, and we will consider this sometimes later. Now, how to design combinational circuits? There are two approaches to design combinational circuits. The first approach is using gate-level design method, and the other one is using block-level design method. In gate-level design method, we make use of the logic gates. After we simplify the function, we use logic gates. While in the block level design, we make use of some functional blocks or integrated circuits. Before we start designing logical circuits, we introduce some terminology. The integrated circuits are classified based on the packing density. ICs with up to 12 gates are classified as SSI devices. SSI is abbreviation of small scale integration. So SSI ICs are integrated circuits that have up to 12 gates. If we go a little bit higher in the density inside the IC, something up to 100 gates, we call these devices medium scale integration devices, MSI devices. Large scale integration devices have up to 10,000 gates inside the IC. Very large scale integration, VLSIs, they have up to 100,000 gates. And there's something called the ultra large scale integration, ULSI, which has more than 100,000 gates inside them. Design objectives. When you design a circuit, what are your objectives? What should be your objectives? The first objective should be to reduce the cost. In order to reduce the cost, you have to reduce the number of gates used. If you are using SSI circuits, you have to reduce the number of the ICs used. If you're using the complex circuits, you have to use less integrated circuit packages. Okay? One of your objectives should be to increase the speed. You have a fast digital circuit. Other objective should be the simplicity of the design. So try to use and reuse the blocks where it's possible. Okay, let's start using gate level design. We have 5 steps in order to design a circuit using the gate level design. The first step is stating the problem. What do you want to design? State the problem as clearly as you can. In this case, we want to design what's called a half adder. We want to build a half adder. What is a half adder? A half adder is a combinational device that adds 2 bits and gives the sum of and the carry on the result. Okay, the second step is to determine the labels of the inputs and the outputs of the circuit. What should you label the inputs? What should you label the outputs? Try to give them names that are related to their function. Here, I named the inputs X and Y. And I named the output S as a sum and C for the carry, because when you add 2 bits, you get a sum and you get a carry. The third step is to draw the truth table of the circuit that you want to design, based on your knowledge of the problem. Okay, this is the truth table for the half adder. these are the inputs X and Y, and these are all the possible combinations on the inputs. Now, if the inputs are 0, 0, and you want to add them, the sum is 0, and there is no carry. If you want to add these two numbers, you will get the sum 1, and the carry is 0. Adding these two numbers will get the sum 1, and the carry is 0. Adding these two numbers will get the sum 0, and the carry equal to 1. Now, the next thing to do in the design procedure is to obtain the simplified Boolean function. From the truth table, we see that C as an output is equal to xy. C is equal to xy. S is equal to x bar y ORed with xy bar, which is actually the exclusive OR of x and y. The next thing to do is to draw the logic diagram of the circuit. Now, this is the logic diagram. You see, there's an AND gate that has X and Y as inputs. And S is an exclusive OR gate that has S as an output. So this is the half adder that we are looking for. Now, if we want to add these two numbers, 4-bit numbers, X and Y, we can add the first two digits. 1 plus 1 is equal to 0, and the carry is equal to 1. 1 plus 1 plus 1 is equal to 1, and the carry is 1. 1 plus 0 plus 1 is equal to 0, the carry is 1. 1 plus 0 plus 0 is equal to 1, and the final carry is 0. Here, we can use a half adder to make this procedure. But for this one, and this one, and this one, a full add is needed. What is a full adder? A full adder, it adds up 3 bits together. So in order to perform this part here, we need something called a full adder, which has an X, a Y as inputs, and Z, which is the carry that is taken from this half adder here. You should add these 3 together to get a sum and the carry. So this is what is called a full adder. We need a full adder here, a full adder here, a full adder here. So now we understand the problem. We need to design a full adder. The next step is to draw the truth table for the full adder. Okay, if you add these 3 bits together, you get a sum of 0 and a carry of 0. Here, the sum is 1, carry is 0. The same is here. Now here, the sum is 0, a carry is 1. The same here, the sum is 1, the carry is 0. The sum is 0, the carry is 1. Now, if you want to add these 3 ones, you will get a sum equal to 1 and a carry equal to 0. Now, let's take the next step and simplify the output functions. Let's see what C here is equal to. C is equal to this min term, which is this one, ORed with this min term, which is this one, ORed with this min term, which is this one, ORed with this min term, which is this one. If we take Z out of these 2 min terms, we will get this term here. And if we take xy out of these 2 min terms, we will get this term here. Now this is equal to 1, so this ends up with xy, and this is equal to the exclusive OR of x and y. The whole thing ended with z. Now, if we take a look what s is, we find out that s is the odd function. It's the exclusive OR of x, y, and z from here. Okay, now we draw the circuit. We draw the circuit as this. This here is S, 2 exclusive ORs. This is XY exclusive OR with Z. All right, and this is S. This here is C, the output. You will notice that these are actually 2 half adders. This is the first half adder connected to the other half adder. the output of the first adder is added as an input to the second adder, and the third input here is the second input of the half adder, the second half adder, and the two carries, the carry from the first one and the carry from the other one, are all together to give me the final carry. So this in is as seen here. A half adder and a half adder. The sum of the first adder is an input to the second adder. The Z input is the second input of half adder number 2. The carry of the first one is ORed with the carry of the second to give me the final carry. So this is the circuit for the full adder. Okay, let's take another example in designing using gate level design. Suppose that we want to design a circuit that gives me the complement of a 4-bit input. These are the inputs A, B, C, D, and these are all the possible combinations that might happen on the input. I want the output to be the complement of the inputs. So the output is W, X, Y, Z. Now this output is the complement of this input. Each output is the complement of this of the corresponding input. This is the 2's complement. Here, this is the 2's complement for this one. Where do we go from here? We start finding out the outputs. Let's take W as an output, for example. This is the K-map for the W output. Okay, this is minterm 1, this is minterm 2, minterm 1, minterm 2, minterm 3, 4, 5, 6, and 7, and 8. Now we start grouping the minterms. We have this green group first, and then we have this group together. We include this one in this group, and this midterm comes in a group by itself, and we result in W equal to A bar C for the green group, and this here will end up with this term. The yellow one here will end up with the yellow term here, and this midterm stays the same. You will notice that A bar is common, so we take it out, and we are left with this term and this term. Now this term here, we can write it in a different way, which is this, from the De Morgan's theorem, okay? And then we notice that this is the exclusive OR of these two terms. So this is what W is. We go to find X. X, if you map it from the truth table into the K-map, you will get these minterms in the K-map. Then we have this group, and this is the second group, and this is the third group. And the terms for the groups are, this one here will result in B bar C, this one here will result in B bar D, and this yellow group will result in BC bar D bar. And this is equal to, finally, the exclusive OR between these two terms, because here we took B bar out, and then this one we expanded it this way. So this is X as an output. If we map the output Y into the K-map, we get these two groups, and from these groups we get the first term for this group, which is C D bar, and the second term for this group, which is C bar D, and this of course is equal to the exclusive OR of C and D. Now you can try to find out the output Z from the truth table, and you will find out that Z is actually equals to D. These are the final outputs W, X, Y, Z for the device that I'm looking for. And if I draw the circuit for these outputs, I will get this circuit. So this is a 4-bit 2's complementary where you put the inputs A, B, C, D, and immediately you get the 2's complement of this input at the output W, X, Y, Z.